This lesson's about position, velocity, and acceleration, something that we've dealt with several times, so this should be a review for a lot of you. I'm going to dive right in. We've done a position function before where a particle is located along the x-axis. So this is a little bit of particle motion. You roll a ball back and forth, you have a position given by a function, and this is asking the question, what is the position at these 4 different places? Well, if I want to figure out what s of 0 is, what s of 1 is, what s of 2 is, and what s of 7 is, S of 0 is easy to plug in. I get 0. S of 1 is also easy to plug in. I get 1 minus 8 plus 10, or 3. Plugging S of 2 in, let's do synthetic division on this. I'm going to put the coefficients of 1, negative 8, 10, and 0. And then I'm going to put 2 and 7, and we're just going to do this with 2. Multiply, add, multiply, add, multiply, add. I get negative 4, which means that S of 2 is negative 4. Now, same with 7. I've crossed that out so I don't accidentally look at it. 7 times 1 minus 8, negative 1. Add, you get 3, and then you get 21. So that is 21. This just tells you the position of the particle at these different time points. Then we move on to velocity, which is how fast an object is moving at any given time, measured in units per time. So distance over time, which is kind of a key thing here, velocity. We have a velocity function, and finding the velocity at these different places is a matter of saying v of 0, v of 1, v of 2, and v of 7. We're going to do the same thing. Plug in 0, I get 10. Plug in 1, I get 3 minus 16 plus 10 is negative 3. Plug in 2. I'm going to do synthetic division on this because I'm also going to do 7, so I might as well just do the same process. So 2 and 7, bring down the 3, multiply, add, and multiply and add, and I get negative 10. And then 7, multiply, add, and add, and I get 45. So given that all of these units now are also in feet per second, which is crucial to understanding what's really happening with this. Now, velocity is a vector, meaning it has both a direction and a magnitude. When velocity is positive, the object is moving in a positive direction, typically upward if we're talking about the y-axis, or to the right if we're talking about the x-axis. When velocity is negative, the object is moving downward or left. And then when velocity is 0, the object is not moving at all. And this typically happens at mins and maxes because these are also probably going to be turning points. Not necessarily, but they could be. We also use this word speed. Speed is an absolute value of velocity. It's what happens when velocity is stripped of its sign. So the speed of an object going 10 feet per second is the same as an object going negative 10 feet per second. They're just going in a different direction. Finally, acceleration measures how quickly an object changes speed, how fast velocity changes at any time t. And this is measured in things like feet per second, or feet per second squared. In other words, it's the feet per second every second. I know, feet. You guys are all science people, and I am too, but hey. So let's kind of move down. Accelerate. Oh, one more thing. We're really going to be kind of careful about these things about when acceleration and velocity are acting in opposite directions. So I'm just going to put a note here, and we'll get back to this. When acceleration and velocity are acting in opposite directions, we know that means that the object is slowing. And likewise, when they're acting in the same direction, the object is speeding up. Whichever direction that is, as long as it's the same, the object is speeding up. Okay, moving along, the example that we have is for the acceleration of a ball rolling along the x-axis and given by this acceleration function. This particular acceleration function, we can actually just plug in acceleration at time 0 is negative 16. Acceleration at time 1 is negative 10. Acceleration at time 2, if I plug that in, is 12 minus 16, or negative 4. And acceleration at time 7 is 42 minus 16, or 26. So a few little bits here. I know that we've done a velocity and position of all of these, but well, I don't want to get too ahead of myself. Let's keep going. Relationship between the position and velocity and acceleration. We've seen this before. Acceleration is the first derivative of velocity and the second derivative of position. Velocity is the first derivative of position. Finally, our terminology. The derivative of any function is an instantaneous rate of change. So an instant velocity, an instant point. An average rate of change is done over 2 periods, over a time interval, not 1 point, but more than 1. So to do an average rate of change, we have a change in quantity over a change in time. And to do an average velocity, we also need to be really, really careful. Average velocity deals with position. Doesn't deal with velocity. You only need to know position at given points. Okay, let's do some examples. This is back to the earlier example we did. I have s of t is equal to this. So velocity function, v of t is the derivative, 3t squared minus 16t plus 10. And acceleration is the derivative of that, 6t minus 16. V of 10 is something that we plug it in, and I get velocity at time 10, so 300 minus 160 plus 10. That gives me 150 feet per second. And the acceleration at time 10 is a of 10 is equal to 60 minus 16, or 44. Let's put units down, feet per second squared. And finally, the average velocity, as we look back up here, it deals with the change in position. So that is the position at time 10 minus the position at time 0 over 10 minus 0. Position at time 10, we didn't calculate, but we can. That is 1,000 minus 800 plus 100 minus the position at the start, which if I plug in 0, that's minus 0 over 10 minus 0. 900, so this is 200, 300 over 10, 30 feet per second. I didn't even need to know the velocity function to get the average velocity over a time interval. Okay, let's talk about fruit flies. We have a function, a test tube, and a function of the population of fruit flies. So how many originally? That's p of 0. If I plug in 0, I get 2 fruit flies originally. The average population growth in the first 4 days is the population at time 4 minus the population at time 0 over 4 minus 0. So that is 22 minus 2 over 4, or 5 flies per day. On average, 5 flies per day. But then if I do from days 4 to 9, I do p of 9 minus p of 4 over 9 minus 4, which is 32 minus 22 over 5, or 2 flies per day. And then finally, at t equals 9, now we have to do a derivative. P prime of t is equal to, well, chain rule says this is going to be 1/2 times 10 times t to the negative 1/2. So p prime of 9 is equal to 5 over root 9, or 5/3 flies per day. Another example, if I graph the position function of a rock, where this is the position, I'm going to graph it as position versus time. So at time equals 0, I start. I know that this particular function factors into 16t times 10 minus t. So I have zeros at 0 and 10. So this graph is going to go from 0 to 10. It's an inverted parabola. You should know that by the shape that's given. So we can just kind of figure out that we know that the maximum occurs at 5. And I can even plug that in pretty easily right now. 5 times 16 times another 5, or 25 times 16. Or 5 times 4 times 5 times 4, or 20 times 20, or 400. Yeah, a lot of mental math. I did all that without taking a derivative. We can take a derivative. We're going to. I mean, it wants us to do a derivative right here. V of t is equal to 160 minus 32t. And right away, then I see that the max occurs when t is 5. But hey, we already figured that out. And I know that a of t is equal to negative 32. Okay, then it says, what's the speed of the rock after 8 seconds? So this is v of 8, which is 160 minus 32 times 8, or negative 96. So to answer the question, the speed is 96 feet per second, and its direction is down. That's what the negative 96 interpretation means. Then it wants the velocity when it is 256 feet off the ground. So we need to figure out what its time is. So I'm going to plug 256 and set that equal to the original function, 160t minus 16t squared. And if I divide both sides by a 16 and move everything to the left, I'm going to get t squared minus 10t plus 16 equals 0. Factors into t minus 8 and t minus 2. So there are actually 2 points where this is happening. I know that v of 2, and I plug it in, is positive 96. We haven't done that, but we did do v of 8, which is negative 96. That should make sense. It's the same point on the way up and the way down. The speed of the rock at t equals 8. That is v of 8 is negative 96. So the speed is 96 feet per second. So just be careful about how these questions are being asked. Then it says, after how many seconds does the rock hit the ground? That's a question about the zeros of the function. We just graphed that up above. That was 10 seconds. The rock reaches its maximum height anywhere where v prime of t is equal to 0, but we saw that occurs at t equals 5. And yes, you can just use the graph that you did. And you can actually plug in, I know S of 5 was 400 feet, so that is the maximum height. And finally, the average velocity would be s of 8 minus s of 2 over 8 minus 2. It doesn't deal at all with velocity. So 256 minus 256 over 6 is 0. That should make sense because it was the same position, relative position on the way up and the way down. This is a symmetrical graph where t equals 2 and t equals 8, its average velocity, its average rate of change was 0. So that's it. You have a homework that's a worksheet. See you later.